Thanks a lot. Thanks a lot for the invitation. It's really a great pleasure to be here. And indeed, I'm not a particle physicist, so all the detailed particle physics questions you might not ask me because I'm the wrong person to answer them. So what we do in my group and with my collaborators is mainly doing large-scale, so-called cosmological simulations. Yeah, so we construct computer models of the evolution of the universe to figure out the distribution of dark matter, for example, but also properties of galaxies, how galaxies grow, how they evolve, and so on and so forth. We also study alternative dark matter models in these simulations and make various predictions for those. For example, self-conducting dark matter, what I will mention later this week, or various warm dark matter candidates, or now also fuzzy dark matter, which are these ultralight axions. So there's a lot of work going on to simulate also these alternative dark matter models. Yeah? So we essentially take the input, or the input that we take is from the particle physicist, what are the properties of dark matter particles, and then we feed this into the simulation codes to make predictions. And the nice thing then is you can explore how a universe would look like in these alternative models. So you can test how the Milky Way would look like, how the satellites of the Milky Way would look like, how large-scale structure would look like, and all these things. So that is what we mainly do. And you can do very little with pen and paper because the regime that we are looking at is highly nonlinear. So essentially all the work and everything I show today will be based on heavy computer simulations. And by heavy computer simulations, we typically mean that these are simulations which run on, say, 20, 30,000 compute cores for half a year or a year. So that's the typical scale of these simulations. So it's rather expensive to do the simulations, which is mainly because the dynamic range of the problems is very large and because the whole problem is very nonlinear. And it involves typically, especially if you include also what we call baryonic matter, so the gas and the stars and everything. It involves a lot of physical processes, and those are also difficult and time-consuming to model. So this is kind of the background, what we're working on. And so during this week, I will try to cover a couple of topics. So this is a rough outline. So it's, these are just the rough themes that we will be talking about. So today I will probably cover completely this, how we predict the dark matter distribution with simulations. So these are so-called dark matter only simulations where we only model the dark matter in the simulation. And then either, if I have time today, I will also start this dark matter simulation methods section. Otherwise, we talk about this tomorrow to give you a basic idea how we numerically actually do this. So how do we, solve this n-body problem to figure out the motion and the distribution of dark matter. And then I will briefly on Wednesday talk about something which goes beyond the standard methods for dark matter simulations. That is especially important to figure out the small scale distribution of dark matter, which is, for example, relevant for direct detection and indirect detection of dark matter searches. And then I will also briefly talk about non-CDM simulations. And there I will put a specific focus on self-conducting dark matter, which is the main focus my group has worked on over the last couple of years. And there's also some collaboration with Tracy's there. So there's a lot of results that came out of that over the last couple of years. And so I will show you how actually a universe would look like if you have a self-conducting dark matter model. And then towards the end of the week, I will also talk about hydrodynamical simulations. So these are simulations which do not only model the dark matter, but also model stars, the gas in the universe, which is mostly helium and hydrogen, that also models black holes, supernova, and all the other things that are in the universe. So in a very comprehensive model. And these models are these days so good that you can match an enormous amount of data. So for example, you can look at the correlation functions of galaxies as we observe them and compare this to these simulations, and you get an extremely good agreement these days. So we can literally in the computer now create these virtual universes, which are patches of the universes, which are something, typically a cube of 100 or 300 megaparsec cube, which match a lot of the statistical properties of galaxies. So this is what we will discuss in this section. And then probably starting on Thursday already, if not, we do this on Friday, we will have kind of, this will be a bit atypical for a lecture, this will be more hands-on, where you yourself, well, in case you're interested, will run some cosmological simulations on your laptop and analyze it. So I have pre-packed a package actually that you can just download and then install a simulation code with some initial conditions, and you can run this in a couple of hours on your laptop. If you have multiple cores, it might run even faster. And then you can analyze this with Python to make, for example, density slices of the universe, or look at halos or density profiles of halos and so on and so forth. So we will make this a bit more interactive on Friday so that you get a feeling on that. This is especially useful, I think, for those of you who will never work in that field, but just want to get a basic idea how this works in principle. By the way, this leads me to the question, is there anybody who's actually working on structure formation simulations or has anything to do with it? Okay, one. Okay, so this is a very pristine audience in that sense. So that's good. Okay, yeah, as Timon mentioned, it's you know, I'm kind of the outsider here. So, but that's good. So you will hopefully learn a couple of things. So let's then get started, and I will start very slowly because that's not your typical material that you're used to. And so we will first talk about how we predict the dark matter distribution. So how do we actually do this, and what kind of results have we derived? So for example, over the last 5 or 10 years. So what are the most important results that we found? I should say all of this is a bit biased towards my work or collaborators of mine because that's the work I know best of, but I can also guarantee you that it's, you know, for some of this work there's still no better work available because there was no bigger project done in that direction, for example, for predicting the dark matter distribution. So it's hopefully still kind of state of the art in most aspects. So if we do dark matter simulations, so just to give you the general framework, I mean, this is a picture that most of you have probably seen many, many times. So if we do dark matter simulations or structure formation simulations in general, we typically initialize these simulations kind of at the CMB time. Yeah, so we cannot start them at the Big Bang. You know, so we have to look a bit later. And the way how we initialize these simulations is by looking at the CMB, and this gives us an idea about the density fluctuations at early times. So the density fluctuations are related to the temperature fluctuations in the CMB. So this gives us a way how we have to disturb essentially the particles in the simulation to mimic the density field that we are supposed to see or that we are supposed to have according to the CMB. Yeah, so this is kind of the initial conditions of the simulations. And then we run this forward in time, and we typically run these simulations then up to a redshift 0, which is the present day. And so this structure formation then goes through all these phases. So through the first galaxies or the first stars, which appear approximately 400 million years after the Big Bang. The first galaxy is 1 billion years after the Big Bang. And then at the present day, we have then, of course, also the solar system and everything. So the simulations that we do cover this whole range, essentially. Yeah. So there's a lot of people working in this field, and many of them are mainly focused on this late evolution of galaxies, but there are also groups who literally simulate the first stars. Yeah, so they try to understand how the first stars come into existence, just a single star, and what kind of properties these stars have. There are also people who simulate isolated first galaxies, just 1 billion years after the Big Bang. And there are the people like us, which simulate largely this rest, to get millions of galaxies at the present day that we can then compare to observations. And so the key, what we always do is we run these simulations and we get this virtual universe, and then we compare to observations to see how well our model works. Okay, and of course we have now a lot of observations because there are a lot of telescopes and satellites and so on that give us a lot of data. Yeah. How much it varies? Yeah, it's 0 here, and then you know, at redshift 1 it's about half time of the universe. At redshift 2 it's 10 giga-years ago, so that's the rough scale. Yeah. So redshift 2 is actually already pretty long ago. Yeah. So it's a pretty long time. And in cosmology or in these kind of structure formation simulations, we rarely give you the times of a given output of the simulation. We typically talk about the redshift. So everything is measured in redshift typically. Yeah, does anybody know what the CMB redshift is? 100? Who says so? 1100, yeah, okay, good. Yeah. Yeah, it's approximately 1100, so that's this time here. Yeah. Okay, so that's the general framework of how we work. And then the initial conditions come, as I mentioned before, from the CMB, and we have now this fortunate situation that we have these great measurements, you know, which started with COBE and then with WMAP and now with Planck, of the CMB with enormous resolution. We have this enormous angular resolution, yeah, so which you can clearly see here, and that gives us a very detailed picture of the early universe. And that's, of course, important for many reasons, because you can constrain, for example, dark matter and many other things by that. However, for us, it's also very important because it gives us the initial conditions from which we start. Yeah? So this is what we have to feed into the simulation code to have the initial conditions. You know, it's important to have a good model for structure formation, but it's equally important, or actually even more important, to have the proper initial conditions that you feed into the simulations. And that's the only way how we have knowledge about the initial conditions. Yeah, so that's what we then typically use. And as you have also seen, the temperature fluctuations show this nice angular power spectrum. And as I mentioned, we use that to initialize the particles. Of course, there's also a lot of cosmology in that. I will not go into that. You can learn a lot about cosmological parameters from this, but we mainly care about really the initial conditions. I should also mention these simulations. If I talk in the following sometimes about dark matter particles, we have to be a bit careful there, because in the simulation, a dark matter particle is something else from a real dark matter particle. As you know, a canonical WIMP, or you know this better than I do, has of the order of 100 GeV typically, so that's kind of a very canonical candidate. Now, in the simulation, we cannot simulate every individual WIMP, right? It's kind of impossible, because the number is just far too large. So what we instead do, we have so-called macroscopic dark matter particles, which are much, much, much heavier than a real dark matter particle, however, which follow kind of the motion and the phase-space distribution of all the small dark matter particles. So we sample, so to speak, this phase space with some macroscopic particles. Does anybody have an idea how heavy these particles are that we have in the simulations? Do you have any guess? 10 to the 8 solar masses. Yeah, that's for some simulations that's true. So we can go down. Essentially, depends a lot on the simulation, but typically you cannot get much better for these large-scale simulations, at least of the order of 10 to the 5 solar masses. Yeah, so it's really enormous mass compared to the actual WIMP. And so whenever I talk about dark matter particle, don't get confused. It's mostly in the context of a simulation dark matter particle, and those are extremely heavy. Of course, ideally, you want to push down this mass so that you have a better resolution. It's similar to a digital camera where you want to have more pixel. So we want to have lower and lower simulation masses to resolve things better, and that's the whole challenge of these simulations, to essentially increase the resolution constantly. This is why we need bigger and bigger computers, better algorithms, and so on and so forth. Then another thing that we need, besides the initial conditions, is of course the composition of the universe. So this is, again, you should be all familiar with this. After Planck, this looked something like that. We have this large fraction of dark energy, we have dark matter, and we have atoms. Now, dark matter only simulations, the simulations that I'm now talking about, they do not model this atoms component. So we only model the dark matter and the dark energy. And the dark energy is essentially implicitly taken into account in these simulations by solving the Friedmann equation in the background. And so there's a dark energy term. And the dark energy that we simulate is just a canonical lambda term. So it's not, for most of the simulations, or for all the simulations that I show here, it's just a cosmological constant. So it's the easiest thing you can imagine. Of course, there are also some groups who look at things like early dark energy or quintessence models or other things. You can all feed this in these simulations to explore this, but the simulations I'm talking about really just only use a cosmological constant. So the easiest thing you can think of. Then as you also know, for the dark matter particle, we have different candidates, with a likely candidate or a good candidate being, for example, the lightest supersymmetric particle, like a neutralino. It could also be an axion. So for the outcome of these simulations, it really doesn't matter too much whether it's a neutralino or an axion, at least for the simulations I show here, because the scales where those differ are just such small that we cannot resolve them in the simulations anyways, and they are not relevant for galaxy formation or for structure formation in the first place. So they, at least for the simulations that I show here, they are just, the clustering difference between an axion and a neutralino is just too small to be resolved in these simulations anyways. However, it is important that both of these candidates behave like a cold dark matter candidate. So it would be very different if the initial power spectrum that we feed in the simulation would be of the kind of a warm dark matter model, because then you would really severely suppress structures on small scales. And as you might know, so-called Lyman alpha force measurement tell us, the constraint essentially the mass of a warm dark matter candidate, and so you cannot make this too extreme because otherwise you erase too much small-scale structure. So the simulations I show here, especially in the beginning of the lectures, is really cold dark matter simulations. Yeah. And then it really doesn't matter whether it's an Axion, a neutralino, or whatever cold dark matter candidate you have. From that point of view, the simulations are kind of agnostic whether you have an Axion or a neutralino. Yeah. I should, however, of course, if you're interested in the very smallest structures that can form at the very earliest times, then it matters. But again, this is not resolved in these simulations. Okay, so now if you put all this together, if you take your initial conditions, if you take essentially GR to solve the equations of motion, which in our case is just a simple Friedmann model, and if you take into account the composition of the universe in terms of dark matter and dark energy, and if you sample the dark matter distribution with these heavy dark matter particles, and you put this all on a big computer and solve the equations from the initial time to redshift 0, then eventually you get something which looks like this. So this is, I'm sure some of you have seen this before, this is one of these typical dark matter density distributions from the so-called Millennium 2 simulation, which was run by Mike Boylan-Kolchin already a while ago. And what you see here is actually the typical outcome of all these cold dark matter simulations. They lead to a very generic outcome, which is the following, that you have these high overdensity. So the color coding here is according to dark matter density. So you have a very high overdensity, for example, here, or at all these knots. And these knots, so these high density concentrations of dark matter, is what we call dark matter halos. And so these are nearly, not perfectly, but nearly spherical concentration of dark matter. And the basic idea is that galaxies, like the Milky Way or Andromeda, they form at the centers of these halos. You have a question? Or?
Yes, sorry. So this simulation was done assuming just lambda CDM, not interacting with dark matter, within the dark matter?
Yes, it's a lambda CDM simulation, yeah.
And what size are the subhalos here? Is it all the megaparsecs or is it all the kiloparsecs?
So well, it depends which halo you are talking about. So for example, so this halo here is a very massive halo. So this is a kind of a cluster, so probably a few times 10 to the 14 solar masses. And with a radius of the order of a megaparsec or so. Yeah. Of course, you have other halos here which are smaller. So there are also a lot of Milky Way-like halos here. So the Milky Way has a, well, at least this is what we think, has a very radius of the order of 150 or 200 kiloparsec. And a lot of these halos are also in this simulation. Yeah. And so there's a lot. So the point is that all these knots are actually dark matter halos, and they are nearly spherical, and they are the formation sites of galaxies. Yeah. And you can also see here that this box has a side length of the order of 100 megaparsec. And so that's a typical size of this simulation. It's essentially a cube, periodic cube, with 100 megaparsec side length. And you have to make this periodic because it's supposed to mimic the isotropic and homogeneous universe. Yeah. So, and we will see this more tomorrow if we talk about technical details, but essentially how you do this, you do on large scales here FFT, which is periodic to solve the Poisson equation, and then you get the periodicity essentially for free in the simulation. Yeah. It also means if a particle runs out of the box here, it comes back in here. Yeah, it's a typical periodic simulation. You can also then guess that your box cannot be too small, because otherwise, you have to take a box size which is such that you're really on the kind of homogeneous scale of the universe, which is at least 100 megaparsec, if not a few more, right? So that is what you have to use.
So this is 100th of the size of the universe, like is it Hubble?
Yeah, if you talk about the Hubble volume, yeah. Mm-hmm. And what you also see here in this picture is, there's also a zoom in shown here of the central region. And you can see that there's a lot of substructure, actually. So all these halos that we have, these nearly spherical objects, they have also so-called subhalos. And in the Milky Way, for example, the subhalos, at least the more massive ones, they host the dwarf galaxies, so the satellite galaxies, like Sagittarius and all these, the LMC or the SMC, so the Large Magellanic Cloud or the Small Magellanic Cloud. And so every galaxy has to sit, essentially, according to that model, in a dark matter halo, also the Milky Way. And it's kind of interesting because these halos are much, much larger than the actual galaxy. And so the Milky Way, we are 8 kiloparsecs away from the center of the Milky Way, but the halo has an extent of the order of, as I said, 150 or 200 kiloparsecs, so it's much, much more extended. Yeah. So it's just a very large object. Okay, so this is And what you also see here are these voids. Yeah, so they're also very underdense regions. This is simply an effect of gravity. Gravity pulls things together, and if you accumulate matter in some region, then you just have to get rid of matter in other regions. So you also get these typical void-like regions here. And the whole thing that you see here looks a bit like web structure, and this is essentially what's called the cosmic web, which is revealed by all these cold dark matter simulations. Now you can not only look at the redshift 0 distribution, but you can also look at at earlier times, like at redshift 1, where we have roughly half time, then at redshift 2, which is something like 10 giga-years ago, and then even at very early times at redshift 6. And what you see here, if you go back in time, the whole thing becomes smoother. And so we start with a rather smooth density field. So the CMB essentially is also rather smooth. So you see always these blue-red colors in the CMB images, but you should not forget that these are 10 to the minus 5 fluctuations, so it's really rather smooth. Also, the density field at very early times, when we initialize these simulations, are extremely smooth. And then essentially gravity amplifies overdensities, and this is how the whole structure formation then works. Yeah. And you can then nicely see how this gets more and more clumpy towards redshift 0. Yep. So
when you say voids, how? What is the ratio of density of the void versus?
I'm actually not sure. I mean, it depends a bit on the position in the void and also how large the void is overall. I'm not sure. I would need to measure this, but they can be quite underdense. Yeah. Also, the density contrast in dark matter, for example, at the center of a Milky Way halo, can be also extremely large. It can be, for example, of the order of 10 to the 6 or 10 to the 7. So it's really very high, the density contrast. And that's also the reason why the problem is so highly nonlinear. So essentially, you can study structure formation at these early times also reasonably well with linear theory, especially, for example, around the time of the CMB or before the CMB. There's no need to do these kind of numerical simulations because linear theory is still very good. So the delta, which is essentially the overdensity, is still rather small. It's much smaller than 1 typically, and you can treat this all analytically. However, the delta at the centers of these halos can be millions or many millions or tens of millions or hundreds of millions, depending on the halo. And then it becomes really nonlinear. And this is why we need these simulations, essentially. Yeah. Okay, and then what you can also do, you can simulate much larger volumes. So this is a bit more recent work from Raul Angulo, who ran also Millennium Simulation, which is called Millennium XXL, which refers to the size. Now you see here this length scale, that's already gigaparsec. So that's a pretty large volume now, yeah. So you have a question? Yep.
So they're three-dimensional real-time simulations,
Mm-hmm.
right? Is there an analog of a mesh size thing?
Okay, so I actually forgot that I have to repeat the questions. So the question was whether there's an analog of a mesh size in these simulations. So talking about the dynamic range and so on. So it's true, the dynamic range is very large in these simulations. So typically it's of the order of 10 to the 6 or 10 to the 7, the dynamic range. It's really rather large. So the spatial scale that we resolve, I mean, it always depends on the simulations, but for this simulation that I showed before, this Millennium 2 simulation, it's typically of the order of a few kiloparsec. What's the smallest resolved scale that we can really resolve in the simulation, yeah? And the overall scale that we simulate is 100 megaparsec. So this is where the dynamic range comes from. So these are not mesh-based, yeah. Yes. But these are not, we don't have a mesh. I will talk more about this tomorrow, but we don't have a mesh lying on top of that because the algorithm that we use is a combination of a mesh for large scales and a so-called tree algorithm for small scales, which is much more adaptive for the scales. So it's a so-called tree PM, tree particle mesh method. And that makes it, that was kind of a breakthrough a couple of decades ago to really do large dynamic ranges. Because if you would just do a regular mesh here, then you are absolutely right, it would be extremely challenging to put such large meshes on the computer. But that's not the way how it's done. So for example, the mesh here is much smaller than what you would really require to resolve these smaller scales, because it's a combination of a tree and a particle mesh code. Yeah. There was another question somewhere? Or? So the question is, what's the typical number of particles? So So the simulation I showed before, this one here, this had of the order of 10 billion particles. This simulation here is of the order of 300 billion particles. And the latest simulations, so latest dark matter only simulations, have now trillions of particles. So this is, and I will come back to this on Thursday also, so this is really growing exponentially essentially. So you can plot actually the size of, the number of resolution elements versus time, and you get an e-folding or a doubling time, which is faster than Moore's law actually. Yeah. Because there were also a lot of algorithmic improvements in addition to computing power. So it's really growing rapidly. And if you look at the literature in the 70s or so, these kind of simulations were done with thousands of particles. And now we are in the multi-trillion range. So it's really was growing a lot. Yeah. Which is mainly due to the computing power. Yeah. So this, if you think about this, if you take, for example, telescopes, the telescope power has not improved so much. This is a largely effect of growing IT and faster computers, essentially, which doesn't affect telescopes so much. So in this sense, the simulation business is really growing much faster, at least over the last decades. You have a question, or? No, okay. Any other questions? Okay. So anyway, so this is now, as I said, a very large simulation with approximately 300 billion particles. And again, you can zoom in here to see the detailed structure. So this is now a very massive cluster of a few times 10 to the 15 solar masses, which is about the largest clusters we have in the universe. So a few times 10 to the 15 solar masses. And again, you can see that it has a lot of substructure here. So this is, again, the canonical prediction of these simulations. Now, the nice thing about these simulations is you can not only look at these images, but you can really put yourself in the volume and then fly with, I don't know with which speed this is. I'm sorry that this runs a bit slow, but you can fly with thousands of times the speed of light or whatever you like to look at the distribution. And what you see if you fly through this, you see this enormous amount of halos. Yeah? And for many of these halos, if they are massive enough at least, there will be a galaxy at the center of these halos. And we flying here towards a pretty massive cluster, and then we will kind of rotate around it. And also in this cluster, which is this whole thing here, you see an enormous amount of substructure. And again, all this substructure can, in principle, if it's massive enough, can host a galaxy. So this is, for example, how the Virgo cluster or the Coma cluster are large clusters or large galaxy clusters which host a lot of galaxies. And their dark matter pendant, although we cannot observe this directly, but indirectly through lensing, for example, would look something like that. So this is kind of how we envision the dark universe. So this is the basic idea. And again, this is now taken from this simulation, this Millennium 2 simulation, which had these 10 billion particles. And you can also see the density peak here, which is directly at the center of this massive cluster. Okay, now when you run these simulations, of course, you do not only want to make pictures and so on and so forth, but you really want to learn something about structure formation. And a very basic quantity that you can look at is the so-called halo mass function. So what is a halo mass function? Well, you can imagine that you have your universe or your volume, and you have dark matter halos of different masses there. You can have very massive halos, for example, the clusters, which have 10 to the 15 or 10 to the 14 solar masses. And you can have low mass halos. For example, the Milky Way is supposed to sit in a halo of the order of 10 to the 12 solar masses, and dwarf galaxies and below are supposed to sit in these 10 to the 10, 10 to the 9 solar masses. And then the question you can ask is, what is actually the number density of these halos? How many of these halos do you expect at a given epoch or a given time in the universe? And that's encoded in this halo mass function. So this shows, as a function of mass, over a pretty large dynamic range here. So if you look at this is kind of 8 orders of magnitude here. So it's really a pretty large range. And it shows you then kind of the number density, or, well, this is multiplied by m, so it's solar masses per megaparsec cube. But if you would divide by m, you would see a number density, so halos per volume, as a function of redshift. So this is shown for 2 redshifts here, 6.2 and 0, so the present day. And you can see there's a clear trend here, which is that you have a lot of the small structures already available at early times. Yeah, so things don't change much here. But then you move this whole thing up here. And so this is the canonical prediction also of CDM, that you grow essentially from the bottom to the top. So you first create the small objects, and then the larger objects come into existence essentially mostly through merging and accretion of smaller objects. So that means that the big clusters, like Coma and Virgo and the 10 to the 15 solar mass clusters that you have here, they only form formed rather recently. So this is essentially encoded in this halo mass function here. And so that's one of the most basic predictions of these simulations, to know how many halos you have in a given volume of a given mass. And you can also see here that there are two lines here, there are two point sets. So red and blue, this is just combining essentially two simulations. So the Millennium Simulation is a rather old simulation, but it is very famous. So that was done 2005 and 6 by Volker Springel, and that had a volume of half a gigaparsec, so 500 megaparsec cube. The Millennium 2 had a 100 megaparsec cube, and you can combine them essentially to increase the dynamic range here, so that you really cover here 8 orders of magnitude in dynamic range of the halo masses, which is quite a lot. Of course, you could then also, which is not done here, but you could also add here the Millennium XXL to get better statistics here, because you see here the error bars. This is essentially these are Poisson errors because we don't have so many clusters in this 500 megaparsec volume because they are so rare. So these are rather rare objects. Yeah. So this is the kind of one of the basic predictions of these simulations. Another thing that you can do is you can then also try to compare this to observations. Yeah, so this universe that we simulate should ideally look like our universe, and this is from the Nature article of the Millennium Simulation. So what you see here is various galaxy surveys which tell you, the kind of the redshift of a galaxy and its kind of position on the sky, more or less, in these pie charts here. So these three are essentially various surveys. And then in red, you see the simulation prediction. And this is just, a qualitative picture, but if you look at it a bit by eye, you see that the clustering behavior roughly, you can do this much more detailed, but the clustering behavior looks rather similar between the two. Yeah? So there's no clustering signal in this data, at least looking at it by eye, that looks very different between the red points and the blue points. And you can do this in much more detail statistically, and you find the same answer, but that's just a nice way of seeing this visually, that the clustering signal is very similar. And in fact, if you look at two-point correlation functions in the most recent simulations, and again, I will show this on Thursday, and compare this to two-point correlation functions of state-of-the-art galaxy surveys, you find, over a large range of galaxy masses, you find nearly perfect agreement. So that means that the lambda CDM model, leads to a galaxy clustering which is in really amazing agreement with the observational data. So this is why if you read papers about cosmology or structure formation, it's always one of the first sentences is usually that the lambda CDM model is a great success for describing galaxies on large scales. It's the large scales because the large scale clustering agrees so well. Yeah. So any problems with the lambda CDM model that we might discuss come mostly on small scales, on the Milky Way scale or dwarf scale or below that. But on large scales, we are now pretty confident that the lambda CDM model is a very good description of the universe because it describes the clustering signal extremely, extremely well. Yeah, so there's not much debate of lambda CDM being correct on these scales. Yeah, so that's kind of accepted. And simulations were kind of instrumental to really show this. And in fact, the simulations were always instrumental. If you look, for example, in the 80s, it was also simulations that essentially ruled out the hot dark matter paradigm. So some of you might know that in the 80s there was a large debate between the Russian school and the American school, kind of whether the universe is filled with CDM or HDM, which is hot dark matter, for example, a neutrino. And a neutrino, since it's a kind of relativistic species, would lead to very different structure formation. So it would essentially create first the big structures and then the small structures. It's just the opposite of the cold dark matter paradigm. And what people then did in the 80s with the very first N-body simulations was essentially to simulate a neutrino universe versus a cold dark matter universe, and making exactly these pictures. And then they compared these pictures to this CFA2 survey. And just by looking at the pictures, you could immediately see that the neutrino-dominated universe looked completely different than the real universe. So that was one of the important pieces that kind of led to the fact that cold dark matter must be the right idea and that the neutrino-dominated universe is the wrong idea. Yeah, so that was a very important piece of work to rule out essentially hot dark matter as the main component for structure formation. Today there's still a debate whether it's warm dark matter or cold dark matter, but you know, the window for warm dark matter candidates is also getting smaller and smaller, so it seems that the cold dark matter might be the right candidate. Okay, now another thing that you can do is, and that is shown in this movie, is you can not only look at the large scales, but you can also look at the Milky Way halo in detail. And this is shown in this simulation. So what you see here is, and this is indicated already by these scales, this is kind of 500 kiloparsec here. You see here the time running and the redshift running over there. And this shows the formation of an individual, just a single dark matter halo, which corresponds to a dark matter halo of the Milky Way. So it has a mass of the order of 10 to the 12 solar masses. The virial radius, so the radius of this object, is of the order of 200 kiloparsec. So it's very similar to what we think what the halo of the Milky Way should look like. And it shows you the full time evolution, how this halo comes into existence. And you see this web-like structure again, and then at the center here you see this material streaming into the halo. This is how dark matter streams into the halo and essentially builds it up. Yeah, so it's only 10 to the 12 solar masses at redshift 0. So at earlier times it's you know, it doesn't have that mass yet, so it's slowly growing, but you can clearly see how all this material is accreted. And you can also see, again, this enormous amount of substructure that is falling in. So some of the substructure is actually disrupted by tidal forces. Some of it survives until the present day. Yeah. So this is essentially how we envision how a dark matter halo that corresponds to the Milky Way halo would form. And this, although the simulation is quite old now, is still kind of one of the highest resolution simulations. So this has kind of 1 billion particles in total in the high resolution region. So it's, but just concentrated on a single halo. It's not a huge volume. It's just a single halo. So what you see here. And you can also see here at the center this very high density peak. So this is this very high overdensity that I mentioned before. You can also see, although I mentioned that the halo is roughly spherical, that it's not perfectly spherical. It's a bit hard to see here, but all these halos are a bit aspherical, so they can be prolate or plate, depending on the exact formation history. So they are never perfectly spherically symmetric, but roughly, roughly that's a good approximation typically. And you can see now we are now at 10 gigayears, so it's close to redshift 0 now. And this is now kind of the final configuration of the halo. And you can see that there's this enormous amount of substructure. In fact, if you count the resolved substructure in these simulations, you see that within 200 kiloparsec or within 300 kiloparsec, you have of the order of 300,000 subhalos resolved in these simulations. So it's just an enormous number. Okay. Yeah. The colors, they encode essentially the velocity dispersion of the dark matter particles. So it's a velocity measurement. Yeah. So these, if you have a halo here, then the particles move around into these halos, and they have some bulk motion, but they also have some dispersion around that bulk motion, and the dispersion is shown by the color essentially. Okay. Now, how are these simulations made? So as I said, these are different simulations. So these are so-called zoom-in simulations. So if you look at the literature, you will often find either these uniform volume simulations or so-called zoom-in simulations. And the difference is that for uniform volume simulation, you always put all your computing power at this full volume, like 100 megaparsec cube or a few gigaparsec cube, as I showed before. However, for zoom simulation, you take one small region here. In this case, just a region that makes up a Milky Way halo, and put all your computing power in this small region. Because you're only interested in this single object, and you want to resolve it as good as possible. So you put all the computing power on that, and this is shown here. So you take this tiny region here, which corresponds to that, and then you put more and more particles there. So this is just here increasing the particle number by factors of 8 always. So you have this first, which is what we call level 5. Then you increase this by a factor of 8, the particle number, again by a factor of 8, by a factor of 8, until you reach this level 1, which is then the highest resolution. And the movie that I just showed was based on this. And with such a simulation, you can then study the phase space structure of dark matter in a dark matter halo in great detail. You can look at the velocity distribution, you can look at the density profile, you can also look at the dark matter density at the solar position to make predictions for dark matter direct detection experiments, for example, for WIMP searches or Axion searches. You can also look at the annihilation signal here to make predictions of what the gamma ray emission should look like of the sky and all kind of things. Yeah. So this is what these simulations are often used for. Yeah. So, but it's a different technique. It's this so-called zoom-in technique. Yeah. So the particle number in this so-called parent box is actually rather low, and you put all the particles in the zoom-in region. Okay. And what you then can do is you can not do this for, not only for a single Milky Way, but you can do this for a couple of halos. So in fact, for this project, this was done 6 times. So you see here 6 different Milky Way-like halos. They were just picked from different places in the parent box. And then you put all the computing power there, and then you get these 6 different realizations. And it's important to do this because you will always have some what we call cosmic variance or object-to-object scatter, because we never know what is real. We don't know exactly which Milky Way-like halo in this simulation corresponds to our Milky Way. So we want to sample a few to get a handle on the variance. And this is why we had to do 6. Of course, it would be better to have even more. But the problem is that, of course, all these simulations are rather expensive, so you can only do a limited number of those. So 6 was kind of a compromise back then. Now you could do many more, but back then, which was a while ago, this was the best that could be done. None of those is, of course, an exact copy of the Milky Way, because we don't know exactly what the Milky Way halo looks like. They just have the right mass, and they have the, they might also have the right formation history, so they didn't have a recent massive merger event or so. But of course, we don't know exactly whether these are Milky Way halos, but they have the rough properties of a Milky Way halo. And just to give you an idea about the numbers of these simulations, so sometimes there are these tables in these papers that quote various numbers. So just that you roughly know what this is about. So here are different simulations listed by this, names here, AQA1, AQA2, and so on and so forth. So these are just the simulation names. And then in the next column here, it's listed the particle mass. So that's literally the particle mass of these macroscopic dark matter particles. And you can see that for these zoom-in simulations, we can actually go pretty low. You can go off the order of 10 to the 3. And I'm sure if you would repeat this today, you could go off the order of 10 to the 2, so 100 solar masses. Yeah. So that's very different from these uniform box simulations, because if you run a 100 megaparsec box, you would never be able to reach that mass resolution these days with the current computing facilities. Yeah, so this is the particle mass. Then this epsilon, this is something we discuss tomorrow a bit more. This is the so-called softening length in units of parsec. So the softening length is the following. And again, we talk more about this tomorrow. We model the dark matter with these macroscopic particles. Yeah. And the problem with macroscopic particles is that they are supposed to mimic the motion of these 100 GeV particles. That's the underlying hypothesis. But the problem is, if you have a very massive particle, you have another very massive particle, then they can undergo two-body scattering. Yeah, if they get close to each other, then just the gravitational pull, you get kind of scattering effects. And for a 100 GeV particle, for the WIMPs, they should actually behave like a collisionless fluid. They should follow the collisionless Boltzmann equation in phase space. So if you take the macroscopic particles and you don't do anything about it, they will never follow exactly the collisionless Boltzmann equation. However, real dark matter particles do follow the collisionless Boltzmann equation. So to get this, or to correct for that, you have to introduce a force softening. So you cannot just use the Newtonian force between the particles for the gravity, but you have to soften this a bit, such that if the particles get close to each other, that the force becomes 0, so that you avoid two-body scattering in the simulation. And this length scale over which you soften the force is this epsilon. Yeah? So this essentially tells you what the spatial resolution is of these simulations. Because below that you cannot trust your results, because there the force law is changed for numerical reasons, because we have these macroscopic particles and not 100 GeV particles. If we could let the particle mass here go to 0, or to very small masses, like to 100 GeV, then of course this would also approach 0, but that's just the limit, which we cannot yet fully, of course, realize in these simulations. Yeah. So whenever you see this epsilon, that is essentially just a consequence of having macroscopic simulation particles. And you see that this epsilon is actually quite small here. It's 20 parsec. Yeah. So I don't know, maybe for you it looks very large, but it is rather small for these simulations. Yeah. Yeah, not exactly in that way. So you can try to extrapolate these results in various ways. So for example, one way to extrapolate them is, I showed you the halo mass function before, and the halo mass function has a certain slope towards lower masses, and you can, for example, extrapolate this further below the resolution level. However, if you really want to know this, the spatial distribution of dark matter on scales much smaller than this, and this is typically very hard to predict because it's unclear there's no guidance how you should how you would extrapolate the local density field, essentially. It's different for a halo mass function because you get a certain slope. And then you just assume, okay, I mean, this is just an assumption, just a working assumption. You see a certain slope, and then you just say, okay, if I go to lower halo masses, I assume that slope holds, and then I extrapolate. Of course, it could be that that's not true, and that at some scale it slightly deviates from that slope, and your extrapolation might be completely wrong, but at least you have some guidance. However, if you have the local density field, then there's no easy way how you could say, okay, I could extrapolate like this or like that. So it's just not that easy. Yeah. So the best you can do is actually really, push for higher numerical resolution if you want to know more details of the phase space on smaller scales. Yeah. Any other questions? Okay, good. And then you see a few more columns here. This is NHR. That's essentially the number of high-resolution particles. So that's the number of particles in this zoom-in region that you use specifically to sample the Milky Way halo. You can see that this is now a bit more than 4 billion. So but that's just a tiny region that samples that. And then you see this NLR. That's for the whole parent box that you use to sample the parent box. Then M200 and R200. These are the properties of the halo that forms, and how the mass is described and the radius. Has anybody here heard about M200 or R200? Yeah. Can you say? Well, do you know what it is? Or?
It's a scale at which you set your integration of your density, such that it's
the critical density. Yeah. So you want to define a certain mass scale for the halo in a certain spatial extent, and there are various ways to do this. And one way is to say you have a certain critical density in the universe, which is just the density for closure. And then you define M200 as the mass enclosed in the radius within which the average density of the halo is just 200 times the critical density. Now this 200 seems a bit arbitrary. However, if you look at some simple analytic calculations how a halo forms, you get this number 200. It's a very specific scale that comes from the so-called spherical top hat model. So it's not completely arbitrary, but it's just a rough, it's a rough way to quantify a halo, the mass of a halo. And so M200, let me repeat this again, is the mass of the halo within the radius, which is called R200, within which the average density of the halo is just 200 times the critical density. Does this make sense? And the critical density is just the critical density of the universe. It's just a way, because a halo has no natural boundary. Yeah, so this whole halo is embedded in the cosmic web. There is no stop sign at some point. You have to define somehow the mass and the radius of that halo. And so that's extremely popular in nearly all papers that talk about halos, or structure formation simulations, or astrophysics in general. If it has to do with galaxies, they often talk about M200 or R200. Yeah. Good. Okay. So this is a table that you will find actually in many of these simulation papers. And the challenge of all these simulations is, of course, always to push this number up. So there's a constant race for the largest number here. So the group who has the largest number usually has the deepest insight in the problem, because you can just resolve more structure. Okay, once you have this simulation done, then you can extract an enormous amount of quantitative data. And one of the most important things that was realized already in the 90s is that these halos obey a certain density profile. Yeah, so by density profile, I mean a spherically average density profile. So you take your halo, you take the center, which is the highest density peak, for example, or the most bound particle, or whatever you want to use as the center definition, and then you measure the density in spherical shells around that halo. So very simple, right? You just make logarithmic bins, and you measure the mass, and then divide by the volume of the shell, and this gives you a spherical density. And what you get is this curve. Yeah, so this shows you, as a function of radius, the density, just here normalized by the average density. And it's kind of interesting because what you see is that in the outer part, and you can fit this to get this more in detail, you get typically a -3 slope. And the inner part, you get a -1 slope. And so it gradually gets shallower. It is very steep in the outer part, and it gets shallower towards the center. And the interesting part is that you can do this for all the halos in your simulations. And you will always get this result. It's an empirical finding, but it's for all the halos that were ever simulated, they can be described by this. So this is why we believe that cold dark matter, or also actually even some other dark matter candidates like warm dark matter also produces these profiles, that all these dark matter simulations always reveal the same density profile. It's a very stable result. There was never any simulation that led to any significant deviation from that. And you can also see here, if you do this for different numerical realizations, so these are again these different resolution levels, level 5, 4, 3, 2, and 1, which all differ by a factor of, approximately a factor of 8 in mass resolution. You can see that these curves, they are all kind of converged up to these dashed lines. Yeah, so if you have a dashed line, then you see a minor deviation always, but beyond the dashed lines, they are all converged. Does anybody have an idea what the dashed lines mark? What could that be? Yeah, resolution, but which quantity exactly? We had this just in... No, not R200. So the epsilon, exactly. So it's related essentially to the epsilon, a few times the epsilon. Because below that, you cannot trust your results anymore. Right? So this is the scale over which you soften the force law, and then you cannot trust this anymore. But if you're far beyond that radius, a few times epsilon, then you get this perfectly converged result. And in fact, what you then can do is you can fit this. And this is a very famous empirical finding, the so-called Nfw profile that was found by Julio Navarro, Carlos Frank, and Simon White in the 90s, which fits these density profiles extremely well. And they have, as you can see, they have a characteristic RS, which is a characteristic scale radius and a characteristic density. And with these, you can extremely well describe all these density profiles. And you can also nicely see, if you have a very large radius, this asymptotes to a slope of -3. If you have a very small radius, it asymptotes to a radius of -1. Yeah. No, the RS is, yeah, I didn't show this here. So the RS is some value here. It's essentially the radius where the slope is exactly -2. No, it's not every halo has the same RS. So they don't have this. So this is just one specific halo, right? So if you take different halos, they have different RS. Yeah. It's just a free scale radius. So you simulate, or you have tens of thousands of different dark matter halos, and they all have different RS essentially. But the point is that all of these halos can effectively be described by that fitting formula. And that was found in 1997, so it's a quite old result. But it's, I would say in terms of structure formation, is one of the most important results that was figured out over the last 20 years or so. Yeah. Well, there were a lot of people who thought about this, but I think there's still no compelling explanation why exactly that profile should look like that. I mean, a lot of people have made arguments in one or the other way and tried to explain it, but to my knowledge, there's no perfect explanation of exactly that form. And yeah, the problem is a bit that, it sounds like a simple problem because it's just a gravitational problem, but the physics of gravitational systems or n-body systems is surprisingly complicated. You know, this is, you know, you would think, well, you know, if I have a bunch of particles, I do something similar to statistical physics, and there must be some equilibrium, and I just figure it out, and I should get this equation. But unfortunately, it's not so simple. It's more complicated for these, for these gravity-only systems. Yeah. There is a, if you take the ratio of Rs to R200, which is called the concentration, there's actually a scaling with the concentration and the mass of the halo, the mass concentration relation, which means that effectively this whole thing, so to speak, depends only on one parameter. Because once you have the mass, you have the concentration, which gives you the Rs at the end of the day. So it's surprisingly well how well it fits all these different halos with a very low number of free parameters, essentially. Yeah. Yeah. I mean, yeah, it would be nice to have a perfect analytic explanation of that, but yeah, it's still pending, essentially. Another thing that was found then a couple of years later, this is shown in this plot here, is that if you have a simulation which has extremely high resolution, excuse me, so higher resolution than what was available in the 90s, and you can really probe the very inner parts of the halo. This is shown here. So this is a density profile just multiplied by R square. So it's a slightly different way of showing it, and then it looks like this for the same simulation that I showed before, these AQ simulations. And if you look at them, you find actually that this profile fits the density profile slightly better than that. But that's only true in, you know, that's only relevant in the very inner part of the density profile. So if you're really super interested in the very details of the inner density profile, you should look at that paper and better use this equation. But for the large majority of work that people are interested in modeling halos, so this is still a very sufficient description. So this is why this so-called Nfw profile became more popular over the last couple of years. But again, it's just only relevant if you're interested in the very inner part of the dark matter halo. So the bottom line is that this gives you an empirical description of the density profile of all the halos. So you have now two things already. You have a halo mass function, and you have something that describes the density profile in all these halos. So it's already a lot of information that you can extract, and it's very universal. So the halo mass function tells you for all the halo masses how many halos are there, and this tells you how their internal structure looks like. So you don't have to run simulations anymore to do this, right? Because you know that that's the density profile. And this is just the point that I made before. This is just a comparison between the residuals of different density profiles. So this is this Nfw, this is the Nfw, and you can see, you know, there are some deviations here in the Nfw, and the Nfw typically does better. But again, you know, for astronomical standards, these are not enormous deviations. So the Nfw is still a very good description. Okay. Then beyond the main halo that we just discussed, which is this thing which is 150, 200 kiloparsecs large, and which has a mass of 10 to the 12 solar masses, there's also all these subhalos. And in fact, there's a whole nested hierarchy of these subhalos. And so if you take, for example, the simulation and look at these subhalos here, and then you get these pictures, and you can see that the subhalos themselves have again subhalos. And you can then zoom again into these subhalos and keep zooming and zooming down to the resolution limit of the simulation. So there's a huge variety of these subhalos and an enormous amount of the subhalos. And as I mentioned before, in this simulation there are 300,000 subhalos. And this, in fact, led to a very big problem at the end of the 90s that some of you might know. Does anybody know what was the big problem with the subhalos end of the 90s? Any idea? Yeah, the missing satellite problem. So what that means is that people in the 90s could run already these simulations, and they could resolve these subhalos. So they looked at the simulation output and saw many subhalos, not 300,000, but many. And then you look at the sky, and you see that the Milky Way has just, you know, of the dozens or so observed satellites back then. And so clearly not this number of thousands or tens of thousands of subhalos. So there's a problem that the number of subhalos that the dark matter only simulations predicted was much, much larger than what is actually observed. Because if that is right, and every subhalo hosts a galaxy, then we should, on the sky, see an enormous amount of galaxies. But we don't see that enormous amount of galaxies. Does anybody know why we don't see them? What's the solution to that? Yeah, they don't have galaxies, so why don't they have galaxies? Yeah, they have a very low escape velocity, exactly, and if you have things like, for example, heating through radiation, which happens during the evolution of the universe, or if you have so-called supernova feedback, so supernova going off in these small galaxies and injecting a lot of energy, you can unbind a lot of the gas and you can stop star formation. So they never make it, essentially, to form a big galaxy. So this is why there might be 300,000 of those, but only a tiny amount of those really make galaxies. Only the heavier ones that can keep the gas, essentially, in them. So this is kind of the solution to this missing satellite problem. Okay. Now, with the subhalos, you can also look at the abundance here. So this is now similar to a halo mass function that I showed before, but now showing you the subhalo mass function within a halo, within a Milky Way halo. And you can see that this has, interestingly, it has this kind of close to -2 slope. So the dashed line is a -2 slope here. And this has direct implications, that slope, because all these subhalos are dark matter overdensities, and if you are, for example, interested in dark matter annihilation signals, then you know that since annihilation is a two-body process, it goes like density square. So if you have a subhalo of very high density, the annihilation signal goes like density square. These subhalos can contribute quite a lot to the annihilation signal. So that means if you have a lot of those, even if they are small, they can contribute a lot. So it sensitively depends on that slope and how you extrapolate this to the smallest subhalos that we think can exist, how much that actually contributes to the annihilation signal. Yeah, so this is why quantifying that slope and quantifying the subhalo mass function has direct implications for any kind of annihilation searches. Does anybody know what's the smallest subhalo mass that we expect for a neutralino? Anybody know that? What's the smallest halo you can form with a neutralino? Roughly? Yeah. Yeah, 10 to the -6. How much is that in Earth masses? Yeah, good, okay. Yeah, it's roughly Earth mass, yeah. So that's the kind of the limit. For Axion, it's much lower, but that's kind of the mass. And you can see, so let's take this 10 to the -6. We are essentially 10 orders of magnitude away from that. You would need to extrapolate this much further. And then you can see that it makes a significant difference in the number of substructures and the number of, and the boost factor, whether the slope is -1.9 or whether it's -2. Because you have to extrapolate this further over 10 orders of magnitude. So this is why people, still today, of course, are very keen in quantifying in detail that slope. Yeah? Because it has a severe implication on any kind of annihilation predictions that we could, for example, observe through gamma ray emission. Another plot also quantifying the subhalo abundance is shown here. Here is a function of radius, the cumulative mass in subhalos, just to give you an idea how much mass is actually in these subhalos. We just said there are a lot of them, 300,000, but you can see that their mass fraction is typically between 10 and 20%. So if you average with, or if you count within the whole halo. So if somebody ever asks you what's the mass fraction in subhalos, a good number is always 10 to 20%. That depends a bit on the halo, of course, but roughly it's 10 to 20%. Yeah, so that's the typical number. Another thing you can extract from the simulations, and that's different from what we said before. So before we quantified the density profile, but you can also look at the velocity dispersion of the particles. Yeah. So the phase space of the particles is, of course, made up of their distribution, their density, and also of the velocity structure. And the velocity structure is kind of quantified here by this velocity dispersion profile. So this shows that each radius here, a log r, shows you the logarithm of the velocity dispersion in kilometers squared per second square. And what you can see here, and again, this is a canonical prediction of all these simulations, that the halos are kind of cold in the outside, then they get hot, and then they get cold again. And so you always have this result. And here it makes a huge difference whether you have a different dark matter candidate or not. So for example, and we will see this later this week, for a self-inducting dark matter candidate, you will actually have a nearly isothermal profile here. So this velocity structure can be impacted quite significantly by the nature of the dark matter particle. However, for CDM, you will always recover that kind of shape. So that's kind of the canonical description, and again, that's described in this paper in great detail. You can see here also, often in these plots, there's a line marking the actual radius of the halo, which is R200. Yeah. And as I mentioned before, it's always, for these Milky Way halos, in the order of 150, 200, or between 1 and 200. You can see that that's true here. Yep. These ones? Yeah. Does anybody have an idea where those features come from? Where do these hot peaks come from? Yeah. Sorry? No, it's not really baryonic physics because they don't even include baryons, these simulations. This is a dark matter only, really. Any other ideas? So what this actually is are subhalos. Now you have subhalos orbiting the main halo, and if they get close to the center, they feel a strong tidal force, so many of them are disrupted, the massive ones. But the massive ones can survive in the outer part. And then you see their imprint, both in the density profile, if you look in detail, and also in the velocity profile here, you see the imprint, essentially, of the subhalos. Yeah. Okay, good. Then another thing that a lot of people are interested in when they run these simulations is actually making more detailed predictions for direct detection and indirect detection experiments. And so as you might know, for a WIMP experiment, for example, the recoil rate, and again, you know this better than I do, roughly goes like this. So you have your local density, then you have this G factor, which is just a function of the minimum recoil velocity, depends on the dark matter mass, and depends on some cross-section. So what you can do with the simulation is, for example, you can evaluate this recoil signal. And you can make predictions of what a detection experiment should actually see. On the other hand, you can also calculate the indirect detection signal, which is an annihilation signal, where you, at the end of the day, you only have to integrate over the density squared, over some volume, and then you have your thermally averaged cross-section, and this gives you directly the signal for indirect detection. So this directly scales with the gamma ray emission, for example. So you can use the simulation to actually extract this information. And before I come to this, I just want to give you an idea how the density at the solar position in these simulations actually looks like. Because if you look at these equations, you see that they strongly depend on the density in both cases. Actually, here it's density squared, here it's density. So we would be in a very fortunate situation, all the WIMP experiments, for example, if the Earth would just be passing through or sitting at a subhalo. Because then the density would be very high, higher than the smooth average of the main halo. So for a long time, or for some time, people hoped that the probability of sitting at a subhalo or in a subhalo is high, because that would immediately mean that the chances for any direct detection experiment would be much higher, both for Axion and for WIMP searches. However, if you look at this in detail, if you look at the density PDF of dark matter at the solar circle, which is shown here, so this is just the density PDF, row over some row model, which shows you the deviation of the densities, you see this kind of smooth feature. And then you see this tail, and this tail comes essentially from subhalos. So this is a tail to very high densities. And as I mentioned before, if we were sitting in a subhalo, we could see this, 20 or 30 or whatever times higher densities compared to the smooth average. So that would be very good for any detection experiment. But what you see in this density PDF here is also that this is extremely unlikely. So the chances of us hitting or sitting in a subhalo is extremely low. So these ideas that the signal could be strongly boosted by us sitting in a subhalo is probably wrong, because all the simulations that we have these days tell us that the probability is essentially negligible. I mean, you can integrate these probabilities. It's of the order of 10 to the minus 4, 10 to the minus 5. So it's really a small probability that we sit there. So we have to live essentially with the assumption that we are somewhere in the average with the density and not just sitting in a high density peak. Now, if you take this into account, then, okay, we know that the density must be roughly the mean density or the average density, but we still have to figure out the velocity distribution. So we also have to measure the velocity distribution of the particles, of the dark matter particles at the solar position. And those of you working on detection experiments or modeling of detection, you might know that there's the so-called standard halo model. people often invoke to make these exclusion plots for dark matter particles in the mass cross-section plane and so on and so forth, which assumes that the halo has a certain density and is described, or the velocity distribution is very well described by a Maxwellian distribution. And so the Maxwellian distribution that's often used here is shown here by this dashed line, and the red line is what the simulations actually predict. And so what you can see is that, if you do detailed simulations, you actually expect a significant deviations from the Maxwellian distribution. This is why, and I mentioned that at many dark matter conferences, why this Maxwellian assumption is just very bad, typically. You can see significant deviations here. And this is not just the outlier of one halo. You can look at this in 6 different halos, the 6 ones that we simulated. And again, if you compare the solid red with the dashed black, you always see the significant deviation. It's never perfectly Maxwellian. And the reason for that is that these halos are not perfectly relaxed. They are not in equilibrium. If you would run these halos for many more tens of giga-years or whatever, eventually they might relax and become more Maxwellian. But it's clearly not the case here, right? So they are just too close to their formation, and there's too much imprinted, essentially, in this velocity distribution due to the formation that leads to deviations from the Maxwellian distribution. So if you want to, in detail, model recoil rates, for example, you should better not use this Maxwellian distribution because it can be wrong by 20 or 30% or even more in some cases. Yeah.
Does this change a lot if you include baryonic effect?
Yeah, there was actually a paper by Mike Kuhn many years ago, and the effect gets a bit weaker if you include baryons. Then you get a bit closer, essentially, to the Maxwellian again. Yeah, that's a good point. Yeah. Okay. Another thing you can do, I guess many of you are familiar with the Dharma result. That okay. So. Which sees these annual modulations since many, many years. So what you can also do with the simulation is try to mock up this annual modulation signal. It's actually not very difficult. You take the Earth in the simulation and just let it go around the sun and let it go around the galactic center and everything, add up the velocities, and then you can make this prediction here. And I don't want to go into too much detail, but it's summarized in this paper, so there's a bit of analysis done there. So this is another thing that you can do. What's also interesting is you can also make Axion Spectra. As you might know, the Axion ADMX and various experiments try to detect the Axion in this microwave cavity. So what this is showing is, again, from the simulation, the power in the microwave cavity versus beta square, which is just V over C, and that relates to the frequency in the detector like this. And again, there's a dashed black line, which is the Maxwellian, the best fit Maxwellian, and the solid red. And you can again see that this is a rather bad description. There's again a significant difference here, especially at low beta, in these Axion detection experiments. And similarly, you can look again at this for the 6 halos, and you find the same kind of deviations, not exactly the same in all the halos, but qualitatively the same in all the halos. And again, this is because the halo is not fully relaxed. Yeah. Okay, and then last but not least, you can also make annihilation predictions. This is from a paper by Vogelsberger. So what this shows you is an all-sky map of the predicted annihilation signal from these simulations. And the galactic center is here at the center of the map. You can clearly see that this is the strongest signal. But you can also see these other points here, which are actually the subhalos. So there's always this question, where do you actually look for the gamma ray emission? Of course, the pristine sites would be the subhalos, because there's very little contamination from other radiation sources. However, they are not nearly as bright as the galactic center. But the problem with the galactic center, as you know, there's a lot of background contamination. So it's just difficult to figure this out. But a lot of people are actually working based on simulations and trying to, kind of predict and measure these annihilation signals and make various predictions for satellites and for the galactic center. Okay, I think I'm done for today, and I guess we should have a few more questions, and then that's it. Thanks. Any more?